the half, almost half of solar radiation is light. So 50% in the form of light. Another 50% maybe at 25% for ultraviolet, and another 25% infrared. So these three components, produce the solar radiation. The radiation emitted by bodies at room temperature falls into the infrared region of the spectrum, which extends from 0.76 to 100 micrometer. The ultraviolet, radiation includes the low wavelength end of the thermal radiation spectrum and lies between the wavelength 0.01 and 0.4 micrometer. Ultraviolet rays are to be avoided since they can kill microorganisms and cause serious damage to the humans and other living beings. About 5% of solar radiation is the ultraviolet range. The ozone O3 layer in the atmosphere acts as a protective blanket and absorb more of the ultraviolet radiation. So 50% is in light. Okay, 5% is in ultraviolet. So meaning that another 38% is in infrared. Okay. So another, this is another example, the application of radiation where we use microwave. Okay, food is heated or cooked in a microwave oven by absorbing the electromagnetic radiation energy generated by the magnetron of the oven. So meaning that the atom inside the chicken, okay, is actually absorb the electromagnetic radiation produced inside the oven in order for the chicken to be cooked. In heat transfer studies, we are interested in the energy emitted by bodies because of their temperature only. Therefore, we limit our concentration to thermal radiation. The electrons, atoms, and molecules of all solids, liquid, and gases above absolute zero temperature are constantly in motion, and thus radiation is constantly emitted as well as being absorbed or transmitted through the entire volume of matter. That is, radiation is volumetric phenomenon. So, figure on the right hand side, radiation in opaque solid is considered a surface phenomenon, since the radiation emitted only by the molecules at the surface can escape. So actually, okay, atoms, electron atoms and molecules of solid, liquid, which is have above zero temperature, is actually emit a radiation. Okay, so beside the bodies, the solid or the liquid emit the radiation, it's also at the same time absorb some amount of radiation. Propagation of thermal radiation, the energy for each quantum E equal to hf. So h again is the Planck constant, which is 6.65 10 power negative 34 joule second, where the Stephen Boltzmann law stated that energy radiated per unit time and per unit area of the ideal radiator is actually EV equal to sigma T power of 4, where the Stephen Boltzmann constant, which is the sigma, is actually 5.7 times 10 power negative 8 watt per meter square Kelvin. Okay. When we talk about radiation, we cannot exclude the black body radiation. This is the ideal case of radiation. Okay. Different bodies may emit different amount of radiation per unit surface area. A black body emits the maximum amount of radiation by a surface at a given temperature. It is an idealized body to serve as a standard against which the radiative properties of real surfaces can be compared. A black body is a perfect emitter and absorber of radiation. A black body absorbs all incident radiation regardless of wavelength and direction. So black body is actually the ideal one. Okay, it perfectly or 100% emit radiation and at the same time it absorbs radiation. So for the radiation energy emitted by a black body, okay, radiation energy equal to sigma T power 4. Okay, this is black body emissive power. Okay, so here on the right side, bottom right figure, okay, we have a black body here. Something wrong with my screen. Okay, so for a black body, okay, the energy being radiated, okay, uniformly, okay, compared to a real body, okay, it has a different value of energy. Okay. A black body is said to be a diffuse emitter since it emits radiation energy uniformly in all directions. Black body at a thermodynamic or absolute temperature above zero emits radiation in all directions over a wide range of wavelength. The amount of radiation energy emitted from a surface at a given wavelength depend on there are two factors, okay, which affect the amount of radiation energy. The first one is the material of the body, okay, and the condition of its surface. And second one is the surface temperature. I mean, which is, we can say F3 lah. The first factor is the material of the body or the medium. Second one, how is the surface, and the third one is surface temperature. So 3. Okay. A black body, the maximum amount of radiation that can be emitted by a surface at a given temperature at a specified temperature and wavelength. No surface can emit more energy than a black body. Because of why? The black body is the ideal cases. A black body absorbs all incident radiation regardless of wavelength and direction. A black body emits radiation energy uniformly in all directions per unit area, normal to the direction of emission. So black body can absorb, then at the same time it can emit. Okay. So we have a graph here, okay, which is the variation of the black body emissive power with wavelength for several temperature. Okay, the wavelength at which the peak occurs for a given temperature is given by when the displacement, which is 2897.8 micrometer Kelvin. So this is the variation of that body. Okay, what observation can we see? Can we obtain based on the graph in the previous slide? The variation of the black body emissive power with wavelength for a several temperature. First one is actually the emitted radiation is a continuous function of wavelength. At any specified temperature, it increases with wavelength, reaches at peak, and then decrease with increasing wavelength. So this is the first statement. So we can see that, okay, it go up and then down. Okay, down. At any wavelength, the amount of emitted radiation increases with increasing temperature. So This is more wavelength. Okay, so this is the temperature here, temperature in terms of energy. So okay, the larger wavelength, so we have larger temperature. As temperature increases, the curve shift to the left to the shorter wavelength region. Consequently, a larger fraction of radiation is emitted at shorter wavelength at high temperature. Radiation emitted by the sun, which is considered to be a black body at 5780 Kelvin, reaches peaks in the visible region of the spectrum. Therefore, the sun is in tune with our eye. On the other hand, surfaces at T less than 800 Kelvin emit almost entirely in the infrared region, thus are not visible to eye unless they reflects light coming from other sources. Okay, so we have here incident light. Yeah. I'm not sure what is wrong with my screen. Okay. So in terms of the incident light, we have red, yellow, green, and blue. So out of 4, 3 are being absorbed, and red is being reflected. The surface that reflect reds, while the remaining parts of the incident light appears red to the eye. The surface that reflect of all the lights appear white, while a surface that absorb all the lights incident on it appear black. So this is why we see things. What color for this thing? What color and for this thing? Let's say a surface that absorb the yellow, green, blue, and at the same time it reflects the red. So in our eye we see it is actually a red color. Okay. For a surface that reflects all the color band, so we can see the surface is white color. While for a surface that absorbs all the color, red, yellow, green, blue, okay, so the surface we can see it in black color, no color actually. Okay, this is another parameter why we talk about radiation is radiosity. The calculation of radiation heat transfer between surfaces involves the total radiation energy stream